Hi, welcome back to NPA Teaching. We have often faced the problems like maximizing consumer utility subjected to the budget constraint, maximizing profit or minimizing cost by producer face several economic constraints in real life, like resources constraints, production constraints, etc. Constraint optimization is probably one of the most common use of numerical methods in economics. These are the problems for which the function is to be minimized or maximized subjected to the constraint. This is not surprising since economics to a large extent is concerned with optimal allocation of scarce resources, and constraint optimization does exactly this. It makes function take its optimal value subjected to the constraints that say what value variable may take. The commonly used mathematical techniques of constraint optimization involves the use of Lagrange multiplier and Lagrange function to solve these problems, followed by checking the second order conditions using bordered Hessian. Now we are going to maximize or minimize a function, that is optimizing a function subjected to a given constraint. So a given function which is the function of x and y subjected to the constraint which is also the function of x and y which is equal to k, where k is the constant. So a new function now we are going to form, that is capital letter F, that can be formed by setting the constraint, that is g of xy which is equal to k. That constraint is equal to 0 and then multiplying it with lambda, where lambda is known as Lagrange multiplier, and adding the product to the original function. Now the new reformed the function will be fxy lambda which is equal to the function of xy plus lambda into k minus g of xy. The Lagrange multiplier lambda approximates the marginal impact on the objective function caused by a small change in the constant of constraint. That is, if one unit increase or decrease in the constant of constraint would lead to increase or decrease the objective function approximately by lambda units. Thus, Lagrange multiplier lambda capture how much change in the objective function due to a 1 unit change in the constant of constraint. Thus, here the reformulated new Lagrange function, that is f, which is the function of x, y and lambda, where the f of xy is the original or objective function and g of xy is the constraint. Since constraint is always set equal to 0, the product, that is lambda into k minus g of xy, is also equal to 0. And addition of the term does not change the value of objective function. Once we've formulated the Lagrangian function, then the next stage is to find the critical value, that is the value of x, y and lambda at which the function is optimized, which are founded by taking the partial derivative of the function with respect to all three independent variables. That means we have to take the partial derivative of the Lagrangian function with respect to x, with respect to y and with respect to lambda, and setting them equal to 0 and solving simultaneously. This is the first order condition for optimizing a objective function with a given constraint. Once we satisfy the first order condition, then the next step is to find the second order condition, which is differ from those of unconstrained optimization, which we are already explained in the previous videos. So the second order condition can now expressed in terms of bordered Hessian, and where the bordered Hessian is the determinant composed of all second order partial derivatives with second order direct partial derivatives on the principal diagonal and second order cross partial derivatives on the of the principal diagonal. which is bordered by the first derivative of the constraints with 0 on the principal diagonal. So from the given bordered Hessian determinant, where f of xx and f of yy, which are the direct partial derivatives on the principal diagonal, and the f of xy and f of yx, which are the second order cross partial derivatives which are on the off principal diagonals, which is bordered by g of x, which is the first order derivatives of the constraint, and g of y with 0 on the principal diagonal. If the bordered Hessian determinant value is less than 0, then the function is minimum, and if the bordered Hessian determinant value is greater than 0, then the function is maximum. Now here we have a numerical example of a function z which we want to optimize. So the function z is equal to 4x square minus 2xy plus 6y square subjected to the constraint x plus y is equal to 72. Now the first step is to set the constraints equal to 0 by subtracting the variables from the constant. So it will become, here the given constraint is x plus y is equal to 72, and if you make it equal to 0, then it is 72 minus x minus y is equal to 0. Now multiply this difference by lambda and add the product of 2 to the objective function in order to form a Lagrangian function. So here the Lagrangian function z is equal to the objective function, that is 4x square minus 2xy plus 6y square, plus then lambda into the given constraint which is equal to 0, that is 72 minus x minus y. After finding the reformulated the function which is known as Lagrange function, then we want to take the first order partial derivatives and set them equal to 0 and then solve simultaneously. So here if you differentiate or take the partial derivative with respect to x, then it will become 8x minus 2y minus lambda is equal to 0, which is the first equation. Then we are again going to take the partial derivative of the given function z with respect to y. Then it will become minus 2x plus 12y minus lambda, which is equal to 0, which is the second equation. Then again we are going to differentiate the given function with respect to lambda. Then it will become 72 minus x minus y is equal to 0, which is the third equation. Now once we find the first order partial derivative with respect to x, with respect to y and with respect to lambda, the next step is to solve this equation in order to find the critical values of x, y and lambda. So from the equation 1 and equation 2, that means if you subtract the equation 2 from 1, then it will become 10x minus 14y is equal to 0. Then if you solve it, then value of x is equal to 1.4y. Substitute x is equal to 1.4y on the constraint, that is x plus y is equal to 72. Then it will become 1.4y plus y is equal to 72, which is equal to 2.4y is equal to 72. Thus y is equal to 30. When you receive y is equal to 30, then substitute on the equation number 4, that is x is equal to 1.4y. Then the value of x will become 1.4 into 30, which is equal to 42. So we received y is equal to 30 and x is equal to 42. Substitute these values on the equation number 1, that is 8x minus 2y minus lambda, in order to find out the value of lambda. So if you solve this, then it will substitute the value of x is equal to 42 and y is equal to 30. Then the value of lambda will become 276. So here x is equal to 42, y is equal to 30 and lambda is equal to 276. Here we can interpret the value of lambda is equal to 276 as if the 1 unit increase or decrease in the constant of the constraint would cause the objective function to be increase or decrease by approximately 276. With these critical values, that is value of x is equal to 42, y is equal to 30 and lambda is equal to 276. Now the Lagrangian function z is equal to, substitute these values on the function, then it will become 9936. Now whether the function is maximum or minimum, we want to find the second order condition, that is bordered Hessian, which we are already explained in the previous slide. That is, the bordered Hessian is the composed of all the second order partial derivatives. So here the f of xx, that means we are going to differentiate again the equation number 1 with respect to x. So it will be 8. Then f of xy, that is differentiating the equation 1 with respect to y, that is minus 2. And then g of x, which is the first derivative of the constraint with respect to x, that is minus 1. Then f of yx, which is minus 2, f of yy, which is 12, g of y, that is differentiating with respect to y of constraint, that is minus 1. Then g of x, which is already explained, that is minus 1, g of y, which is minus 1. Then 0 on the principal diagonal, that is here. Now if you find the determinant of bordered Hessian, then it will equal to minus 24, which is less than 0. Then we can say that the function is minimum. Now we are going to solve the constraint optimization of multivariable functions in economics, that is the solution to the economic problems, which is in the form of maximizing utility or maximizing profit to the budget constraint or minimizing the cost subjected to the sum of the such minimal requirement of output as a production quota. So here we want to maximize pi, that is profit, which is equal to 80x minus 2x square minus xy minus 3y square plus 100y, which is the objective function. That is, here our objective is to maximize the profit subjected to the constraint, that is x plus y is equal to 12. As we are already discussed, the first step is to set the constraint equal to 0, that is 12 minus x minus y is equal to 0. Then multiply by lambda and form a Lagrangian function. So here the Lagrangian function, that is pi is equal to 80x minus 2x square minus xy minus 3y square plus 100y plus lambda into 12 minus x minus y. Now we are going to take the first order partial derivatives with respect to three variables, that is x, y and lambda. So if you take the partial derivative with respect to x, then it will become 80 minus 4x minus y minus lambda is equal to 0, which we set as a equation 1. Then again we are going to differentiate the given function with respect to y, then it will become minus x minus 6y plus 100 minus lambda is equal to 0, which we are setting as equal to second equation. And similarly, we are again going to differentiate the given function, Lagrangian function, with lambda, then it will become 12 minus x minus y is equal to 0, which is the third equation. Now we are simultaneously solve this equation in order to find the critical values, that is value of x, value of y and value of lambda. So for finding these values, subtract the equation number 1 from 2, then it will become minus 3x plus 5y minus 20 is equal to 0, which we are setting as equation number 4. And similarly, we are multiplying equation number 3 into 3, then it will become 36 minus 3x minus 3y, which is equal to 0, which is the fifth equation. Now subtract equation number 4 from equation number 5, then it will become 8y minus 56 is equal to 0, then y is equal to 7. Once we get the value of y is equal to 7, then substitute on this equation number 3, then the equation number 3 is the 12 minus x minus y is equal to 0. Substitute y is equal to 7 here, then x will become 5. Once we received the value of x is equal to 5 and y is equal to 7, then substitute these values on equation number 1. That is equation number 1 is equal to 80 minus 4x minus y minus lambda is equal to 0. Here we are going to solve this equation for lambda by substituting value of x and y on equation number 1. Then lambda will become 53. So once we get the value of x is equal to 5, y is equal to 7, lambda is equal to 53, then the value of profit function, that is objective function, that is profit function here, that is Lagrangian function, which is equal to 868. Now we want to check whether the function is maximum or minimum, because here the objective function is already given, that is the profit maximization. So we want to check whether the given profit maximization function is maximized or not. We want to check the second order condition, that is bordered Hessian, which we are already explained, that is all these second order partial derivatives. So here f of xx, which is minus 4, f of xy, which is minus 1, and g of x, which is the first derivative of constraint with respect to x, which is minus 1. Then f of yx, which is minus 1, f of yy, that is direct partial derivative, second order partial derivative, which is minus 6. Then g of y, which is the first derivative of the constraint with respect to y, which is minus 1. Then g of x, which is minus 1, g of y minus 1, then 0. Now we want to find the determinant of bordered Hessian, which we are already calculated here, which is equal to 8, which is greater than 0. Then the determinant of bordered Hessian is come out with the greater than 0. Then we can say that the given profit function is maximized. Now we are going to consider the last example of the constraint optimization of a multivariable function with its application in economics, that is minimize the cost, that is c is equal to 8x square minus xy plus 12y square, subjected to the constraint, that is x plus y is equal to 42. So the first step, which we are already discussed, set the constraint equal to 0. So it will become 42 minus x minus y is equal to 0. Then frame the Lagrangian function by multiplying lambda. So it will become z is equal to 8x square minus xy plus 12y square plus lambda into 42 minus x minus y. Now we are going to take the first order partial derivative with respect to x, y and lambda. So here if you take the partial derivative with respect to x, it will become 16x minus y minus lambda is equal to 0, which is the first equation. And if you differentiate the given function with respect to y, then it will be minus x plus 24y minus lambda is equal to 0, which is the second equation. And again we are differentiating the given function with respect to lambda, then which will become 42 minus x minus y is equal to 0, which is the third equation. Once we get the first order partial derivatives, then find the critical values x, y and lambda. So for finding this value, we are going to subtract the equation number 2 from 1. Then it will become 17x minus 25y is equal to 0. Then solve for x, then it will become x is equal to 1.47y. Substitute x is equal to 1.47y on the constraint, that is x plus y is equal to 42. Then it will become 1.47y plus y is equal to 42, that is 2.47y is equal to 42, then y is equal to 17. Now substitute y is equal to 17 on equation number 4, that is x is equal to 1.47y, then value of x will become 25. Substitute value of x is equal to 25, y is equal to 17 on equation number 1 in order to find the value of lambda. So here by isolating lambda, then it will become lambda is equal to 383. So x is equal to 25, y is equal to 17 and lambda is equal to 383. These are the various critical values. As we know, our objective function is to minimize the cost. So we want to check whether the given function is minimum or not. For that, here we are checking the second order condition, that is bordered Hessian, and which is the second order partial derivatives. So here f of xx, which is equal to 16, f of xy which is minus 1, g of x which is minus 1, f of yx which is minus 1, f of yy which is 24, and g of y which is minus 1, then g of x minus 1, g of y minus 1, and we are putting 0 on the last element. After substituting these values, now we want to find the determinant of bordered Hessian. And here it is already solved, and we received the value of determinant of bordered Hessian is equal to minus 42, which is less than 0. So we can say that the given cost function which is minimized. I hope you are clear about how to optimize, that is maximize or minimize a multivariable function along with the constraints, which is the use of Lagrangian multiplier and Lagrangian function to solve these problems, followed by checking second order condition by using bordered Hessian method. Have a nice day and see you in the next video. Thank you.